Okay, so there's two things we should have noticed in the video. One, from Donnie's perspective, it looked like Princess Ducky was going way faster than either the moving walkway or the tank would individually. And we could also even see what it would look like from the perspective of the walkway, because you could see Princess Ducky moving relative to the little compass that was on the ground. And so we could see that she was moving along the walkway at a pretty good pace, but then the walkway itself was moving. We could see the compass moving from Donnie's perspective. But the total was that Princess Ducky, from Donnie's perspective, looked like she was going faster than she did just from the perspective of the walkway, and faster than the walkway itself went. And probably not too surprisingly, since she was just driving in the same direction the walkway was going, we can just combine these two velocities to figure out how fast it looked like she was going. From Donnie's perspective on the ground, it looked like she was going 7 meters per second. Which means there's got to be a way, there's got to be some rules for how we combine relative velocities to figure out how a combination of things from different frames wind up looking in a certain frame. So, for relative motion problems, we're generally going to have stuff that follows this form. In our relative motion problems, we're going to be looking at, we're going to be comparing the motion of an object from the perspective, or relative to, a pair of different reference frames. One of those reference frames is usually going to be moving. And a stationary frame. And so since I need my little subscripts, let's use O for the object just in general. That would be Princess Ducky and her tank in this case. We'll have the moving frame, which will be the moving walkway, the people mover in this one. And we'll just use S for the stationary frame, which was the ground in this particular problem. So like Princess Ducky, how fast her tank could go, when we said 4 meters per second, that's how fast the object, Princess Ducky's tank, was able to move relative to the moving frame. So that would be VOM. And when we said that the moving walkway went at 3 meters per second, we mean from the perspective of the ground. If you're on the ground, it looks like the walkway was going 3 meters per second. So that would be the velocity of the moving frame compared to the stationary frame. And we saw that from the perspective of the ground, Princess Ducky wound up looking like she was going really fast. She looked like she was doing the 4 meters per second plus the 3 meters per second. So we must be able to add these together to figure out the velocity of the object relative to the stationary reference frame, which is a new set of subscripts. And so those always add together using these rules. So say we have the velocity of the object compared to the moving reference frame, and then we add the velocity of the moving reference frame compared to the stationary reference frame. That'll always give us the velocity of the object relative to the stationary frame. And there is a method to the way that these subscripts go together. You'll notice first off that these two inside subscripts, so the last subscript here and the first subscript here, these match. So you have the same subscript at the end of the first thing you're adding and the beginning of the second one you're adding. And then the first subscript at the beginning of our addition equation and the first subscript for our resultant wind up being the same. The first subscripts match, and you'll notice that the last subscripts wind up matching. And this is always how relative velocities add together. In fact, it doesn't even need to be specific to an object, a moving frame, and a stationary frame. It could be an object that is moving on some other frame that is moving relative to some other frame, or you could have lots and lots of objects that are being added together. But if you always chain them together, when you add them together, make sure that the last one subscript matches the first subscript of the things that you're adding. Then you'll wind up with your total, your resultant, just having the very first subscript of your chain of things that you're adding together and the last subscript of the things that you are chaining together. And so in our case, so for our example, if the velocity of, let's do Princess Ducky's tank, compared to the moving walkway, she was driving at, we said, 4 meters per second. And she was driving south from the perspective of the moving walkway. And then the walkway, we said, the moving walkway was moving compared to the ground at 3 meters per second to the south. And we wanted to know what was Princess Ducky going to look like compared to the ground. Well, we can write an equation using our subscript rules. So we got to make sure that our resultant, if we're trying to get VPG, that means that when we add our two velocities together, the first subscript in our chain has to be P, and the last subscript, so not this one, but the second one, has to be G, because the very first subscript on both equations and the very last subscript have to match. And then these two inside subscripts, the last subscript here and the first subscript here, they're going to match each other as well. And if we look at our notation, that's got to be M. So VPM plus VMG should give us VPG. If we draw that as a tip-to-tail diagram, so 4 meters per second was VPM. We connect that tip-to-tail to VMG, which was 3 meters per second. And then the resultant from the beginning to the end. So our resultant is VPG. It's going to be 4 plus 3 is 7 meters per second, which is what we saw in the video. It looked like she was going, like we had to combine those two velocities together. So now we're going to look at what happens. We're going to take sort of this like really simple observation of how this works and start thinking about what happens if we start changing the directions, what happens if we start messing with the angles. And so we're going to watch another series of videos, and I would like you to predict what's going to happen in them. Princess Ducky is still going to be moving at, let me post-it note here. So Princess Ducky is going to be heading, and you don't have to write down anything on these post-its. This is just so you know what you're making your predictions based on. Is going to be heading north. So she's going to be driving north. So that is the opposite direction the moving walkway is moving. Maybe she realized she left something at the beginning, or she decides she suddenly doesn't want to go on the plane or something anymore. And so she turns around and tries to drive her tank in the opposite direction the walkway is going. And that's going to be at 4 meters per second. I want to know, what is this going to look like if the moving walkway moves south let's look at a few different things. What if it's going at 3 meters per second? What's that going to look like? What if it's moving at 4 meters per second? And what's it going to look like if it's moving at 5 meters per second? How is Princess Ducky going to wind up moving compared to the ground? What's this going to look like to Donnie as he watches Princess Ducky try to drive backwards on the moving walkway if she goes at 4 and it goes at either 3, 4, or 5? So think about what you think that's going to look like. If you feel comfortable, even maybe come up with a number of like what you think the velocity might look like. And then go ahead and watch the videos. Keep in mind, the videos aren't necessarily perfectly to scale, but they'll at least follow this general idea that one time the walkway will be going slower, one time it'll be going the same speed, and then one time the walkway will be going faster than her tank does.